Okay, so we covered what the model architecture looks like from a diagrammatic point of view. We covered some of the math of the operations like convolution transpose, looking at the loss function, looking at the dice score. And now I think we can start to code. So I have So I have some skeleton code here, some helper functions like using matplotlib to visualize data, um, things like loading and testing the model, loading the config files and stuff. I've already coded all that out. I'm not gonna actually, and I had ChatGPT do the matplotlib code because I hate, yeah, I hate writing matplotlib code with a passion. So um, yeah, I don't want to. I want to make sure these videos are as targeted as possible. So I don't want to walk you through all this boilerplate code. I'm gonna fill in the blanks. I do think it is nice. I do think it is. I could show you the finished product, but I think it is useful to watch someone code through something step by step, which is what I wish I had available to me when I was learning this stuff. Unfortunately, I didn't. So, but that's the gap I'm gonna fill in now. So let's get started. So just to walk you through what's already here, main function, we're gonna load the environment. So I'm creating separate environments, one for local and one for the server when I'm on RunPod or when I'm on a virtual machine with the GPU. As you can see in my previous videos, I was doing a lot of hard coding. I want to move away from that just to move more quickly. And as I record more videos, I'm going to streamline the process even more. But, just to optimize for getting videos out there, you know, I'm going to start with things that are a little bit inefficient and then sort of like as I make more videos, I'll tighten things up. One of the things I'm tightening up now is just, making config files. So I can just, on the server, on the virtual machine, I can just clone the GitHub repo and then, the command that I use to run the code, I'll just run it by passing in the server config file. So it runs all the server configurations and I don't have to do any kind of coding in the virtual machine or I'll minimize hard coding things as much as possible. So, right, so I'm loading the config file here. I'll print the configuration as a dictionary just to make it easy to see, in the output what's being printed. This load config file is obviously code to load the config file. Right, and then yeah, we'll run this for at first. So I need to implement all of these. So I guess we'll right. So first I need to implement configure dataset. And then so the rest of this code is just matplotlib code. I already brought in all the imports. So yeah, let's implement. So basically, right. So basically, where am I? Oh, so configure the dataset, which is simply, yeah, applying any transformations necessary to the data. So it looks the way it needs to look, which it won't be too many transformations. I mean, it's not like I'm using a raw data set in the real world, which requires a tremendous amount of cleaning. But I do need to transform the data. And just, create the training data set, the validation data set, stuff like that. Well, no, this is just transforming the data. The next is visualizing the data so you see what the actual data is. That's always important. I mean, obviously you need to know like you would think it's a no-brainer, but it is kind of easy to sort of, with these toy data sets, just pull something down and run a model on it without even looking at the data, right? But you do need to look at it, so you understand what kind of data you're working with. Then I'm going to split the training data into training and validation, creating actual data loaders. And then this loaded test model is, so basically what we're going to do on the server is we're going to run it and then use weights and biases to save the best model. And then we can load it locally and print out how the model, like, actually visualize the prediction. So we can actually visualize the segmentation masks, which, you know, regardless of what your DICE score is or whatever your metrics are, you want to be able to visualize how your model's performing. That's one of the best, you know, early sort of markers for how your model's performing. Right, and this last bit is, this is already gonna be implemented right here. I'm not gonna actually code that, and in the video at least. And then last is training and validating the model. So I think what I'm gonna do is, do I wanna build the model first? So I think I'm going to do configure data set, get train validation data, and then I'll actually implement UNet, and then I'll start implementing train and validate model until the point where I load the model. Then I'll load the model and see if it all runs, and then I'll do the rest of the training and validation portion. So yeah, let's get started. So configure data set. So I think I passed in a config file. Right. So that returns the data set, right? Yes. So first we need to load the data. And then we'll visualize it after so you see what this is. So this is basically, it's just pictures of pets, of animals like dogs and cats. And yeah, it's the three classes. The three segmentation classes are pet, pet object, background, and then the boundary class. So download, we're going to say false because I've already actually downloaded the data. If you haven't, make sure that's true. Put a root. That's actually something that's going to be in the config file because when it's on the server, it's going to be a different path to the data. So that's something that I want to be configurable. Transform, and then I'll define this target transform. So transform, we're going to add data augmentation. Right now we won't, but later on we will. I might actually cover this augmentations package for now. I think I'm just gonna leave this blank. So transform equals t dot compose. This is the transformation of the labels. So the transformation that we're gonna apply, always, always resizing. We're gonna use, this is gonna be configurable, of course. I'm gonna use 128 pixels, 128 by 128 locally, and then scale it up to like 244 when it's on the server. I have to check and see what size the original data is. I think it's like 244 or something. They're not, the images aren't that big. And then 2 tensor. It's gonna be pill to tensor lambda. So and then okay, so for the target transformation, so right, this is the transformation applied to the training data, or the data. This is the transformation applied to the label. I'm gonna make that a callable function. I could define it as a lambda here, but the reason why I need to make it a function is because it needs to be serialized properly, because there's a certain parameter that I'm going to set on the data loader, which is the number of workers, and also like memory pin to be equal to true. And if I don't make this a named function, it won't be serializable. And there's a reason why I do need to set those parameters on the data loader, which I'll explain when I get to it. It's so there isn't a bottleneck on the server when I'm using the GPU. Basically, the images need to be loaded fast enough so that the GPU can actually perform well. Otherwise, there'll be a bottleneck when the images are loading, when the batch is being collated, and the GPU basically won't really be utilized, and all the load will be on the CPU. So adjust target mask x dot, and so the input dimensions, it's going to be batch 1, and then height and width. We want to, in order for so this adjust target mask. So for the targets, when you call, so the Oxford Pet data is RGB, but the segmentation masks are in grayscale. And when you call pill to tensor, it creates the channel dimension will be basically when it converts the pillow object to an image tensor, the color channel is 1 because it's grayscale, but the cross entropy loss PyTorch's cross entropy loss function expects an object of just it just expects the labels to be, it doesn't expect an extra channel dimension for the image labels. It just expects batch width, height and width, where the values of the pixels will be the labels, the target labels. Also, it expects long. The cross entropy function expects long. So you convert it to a long, then you squeeze out the dimension, and then you subtract. You subtract 1 because so the classes are pet, background, boundary, and that will be, it will be, the list will be 1, 2, and 3, but you have to subtract 1 to set the indices back to 0, 1, and 2. And that's the format that PyTorch expects. So this should be good. Target type. So to run, we do end local Python. I've already created my virtual environment, Conda environment. Actually, guys, I'm going to switch to poetry. Maybe not this video, but next video, next project, I'm going to switch to poetry just because I like it more. Also, another addition I'm using in this project is wandb, weights and biases. So that just makes tracking your project so much easier. So this should, actually I need to run it from one directory up because of how it's coded. Let's see what happens. Target type, I think it's target types. Good. All right, so the dataset gets returned. So, right, running in local. These are all the parameters. It's the seed, CPU, the seed number, CPU, and then it looks like the data set, so we can print. Right, so it's about 3,500 images. So now let's visualize the data. I've already implemented this function, but let's see what it looks like. Boom. So this is what our images look like. So these are our images. We can see the majority of these images will have the background pixels being the majority of the image, except for something like this, right? But most of the images will be like this. So yeah, so these are our images. So I'm gonna comment that out for now. So now we're gonna do get train. Take some data set and config. So what do we do? So we need to split the data set. So first of all, right, so we split it into train length and then a test length. Right, so 90% of the data. Oh, let's see if this runs. Yep. And then we make our data loaders. So batch size, shuffle. Yes, we always shuffle the training data. And then the two important things to add to address the potential bottleneck on the server is num workers. So this is for threading. So we want to make sure that the data loader operation, the data loader process is hyper-threaded so that there's no bottleneck on the server when we're trying to collate a batch. So this is going to be config num workers. It's going to be 4 on the server. I don't know. I think there's like 31 virtual CPUs on the server, so it's going to be like 15. You always set the number of workers to the number of actual cores, not the number of virtual cores. And then Oh, and then we set pin memory equal true. I don't know the exact, I don't remember the exact details of pin memory, but it's basically pinned memory is telling the operating system to dedicate specific memory for this um, process instead of allowing it to be swapped out for disk memory. So it has something to do with paging, but we're telling it to dedicate, set aside, like we're telling it to pin and dedicate certain memory to this operation so it can be accessed more quickly. So we're going to do that for both data loaders and that size. I also want to, so if we're doing a test run, um, so basically we're going to randomly sample indices and then pass those indices to a subset class and create a new data set. This is just for test running locally so we can reduce the size of the data set. Otherwise, it's too quickly to go through a full training epic and we can't validate all of our code. So this should work. Okay, that makes sense. We have the sample size here, test run is true. So now, so all right, so now we'll uncomment this. Test model is going to be false, so we're not going to call this right here. I mean, if we want, I guess we can just leave it blank for now. Wait, no, then the else will fail. Let's just keep that. Train model is going to be true. So train and validate model. So, train and validate model. First, actually, yeah, we're going to initialize weights and biases. So I think it has a project, a name for the run, mode. I think I meant to change the name of this as well. Project name, mode. I think that's it. And also, we need to turn that into a dict first. So, actually, I don't think we returned anything from this. So, let's run this. Okay. So the mode locally is going to be disabled. And then when we go to the server, we're going to kick it online so we can start recording our runs. But locally, we're just going to look at the printouts. We're going to use TQDM to create a nice progress bar and printout so we can view the loss and make sure that nothing crazy is going on before we move into the server. All right, so I think we implement our model next. This is gonna have in channels, out channels. In channels and out channels are both gonna be 3 for this project. So for this data set. Okay, so let's do UNet. First, for UNet, we're gonna do the double convolutional layer. So let's implement that. So So we're going to do the double convolution right here. Yeah, we're going to do convolution rel U, and I'm going to add batch norm. I'm going to normalize the lockets before I send them to the rel U because that's typically good practice. I've already covered batch norm in one of my previous videos, so take a look at that if you want to learn more about it. So we're gonna do super, always gonna do that first. And then self dot, or conv 2D in channels, out channels, kernel size 2, adding 1 for kernel size 3, padding 1 for same padding. Batch norm 2D channels. Place true. Oh. This is going to be out channels to out channels. Boom. That's our double convolution operation. Now, UNet. All right, so let's do the encoder. Let's start working our way down, and I'll make comments on what the dimensions should be as we traverse down the encoder. So okay. So we have our input. Should be batch channels 3 height and width, which in our locally is going to be 128 by 128. So we're going to split it into DoubleConv and max pool, DoubleConv, max pool. So down 1 is DoubleConv, in channels is in channels, out it's going to be 64, just like here. So 64, 128, 128. So the DoubleConv does not change the image size, only the max pool is what downsamples. So we're going to have, I'll exclude the batch from this comment, so it'll just be 64, 128, 128. Or, yeah, let's just say 128. Let's just say it's 128. So pool 1, max pool 2D, kernel size of 2. This is going to downsample our image. If we make a kernel size of 2, it's going to downsample our image. It's going to reduce the dimensions of the image by half. So 64, 64, 64. We're just going to copy that. 64. We're going to increase the channels to 128. 128. 64, 64. And then max pool 2D is going to be 128, 32, 32. right? So the 128, 32. So we went from here to here and then to here. So 128, 64, 64 here to 128, 32, 32 after the max pool. So we're just following the diagram exactly. So 128, DoubleConv is going to increase it. Sorry, we're going to make the out channels 256. So this is going to be 256, 32, 32. And then we're going to downsample our image by half, 256, 16, 16. It's right here. Boom. And now one more. Oh, 3, 3, 4, 4. 56, 512, 16, 16. It's going to be 512, 8, 8. We'll do middle. Eight, 8. Now we'll start working on the up direction. Say up 4. It's going to be conv. So, all right, we're going to work on this green arrow. We're going to start traversing up the decoder. So we need to do the convolution transpose operation so that we can upsample our image from 8 by 8 to 16 by 16, and then also reduce the dimension, the feature channels from 1024 to 512. So transpose 2D, 1024, 512. Kernel size 2. Stride was 2, just like here. Stride's going to be 2, kernel size 2, so that when we plug it into this equation, it doubles our image size. It upsamples by a factor of 2. And then we need to do this DoubleConv refine operation. So we're going to concat. We're going to have a skip connection that concatenates directly from the encoder. So then our dimensions will go back up to 1024, and then we'll refine it back to 512. This is going to give us 512. 512, 16, 16. And this is going to give us the same. So we concatenate, send it back through this, and we get 512, 16, 16. Now we want to get 256, 32, 32. We can just copy this. Let's remove this kernel size. Make it more readable. Well, 32, 32. We can even add suppose output dimensions. HN minus 1 times stride minus 2 times padding plus P naught. Okay. So the very last, so we're gonna have 64 dimensions. So we need to output 3 for the 3 classes, 3 logits for the 3 classes, the 3 prediction classes, right? Conv, so that's gonna be conv 2D, so 64. Kernel size is gonna be 1. This is gonna give us 3, and then 128, 128. Wait, hold up. 256, 128, 128, 64. $16, 32, 32, 64, 64, 128, 128. 1024, 512, 256, 128. One 28, 64. It should be 64. That's 64 to 128, and then 64 to 3. Kernel size is 1, so we don't need padding for it to be the same. Yes. Let's just run this. Should be okay. Well, okay. Yeah, I'm actually instantiating the object, so forward self x. So self dot down 1 x. So we're going to label this. We're going to create a variable so we can pass it as a skip connection. down 1. That makes it easier to see. Down 2. Down 3. Down 1, down 2, down 3, down 4. Middle. Now, here's the fun part. We need to upsample, then concatenate, then refine. Upsample, so convolution transpose, concatenate, fuse, and then refine. So upsample, fuse, refine. Double. So we upsample with up 4. So self.up 4 on M. Then we fuse with D4. This is D4 right here. So we fuse D4. Torch.cat. We fuse along the channel dimension, which is the dimension 1. And then we pass that to the DoubleConv, which is conv4. And that's going to give us, we'll call that U4. Then U3. Two is going to be 1. Replace all the 2's with 1's. 3 is going to be 2. I think I'm good. Self.out U1. Okay. I think this is our UNet, folks. I think this is our UNet. So let's run this. Let's define the criterion. We're gonna do a weighted cross entropy loss because I do think there's a class imbalance. Just eyeballing the images. So we'll define the weights there. And then we're also going to exclude the boundary class in the loss because you're not supposed to be computing loss over the boundary class. It's just something to help you during validation. So the second index is the index of the boundary class, and the weights, we have to make it a tensor, so that, and then we also have to send it to the device to make sure that everything is going to be on the GP on the same device. Tensor. I'm gonna make the weight of the pet class to be 1.3 because there are less pixels devoted to the pet class across, as on average across all images. And then I'll make the background class 1, and then the boundary class 0, although we're ignoring the index, so it doesn't really matter anyways. Device config.device optimizer uh, let me just run this. Okay, weights criterion optimizer. All right. So yeah, so I think this is the basic. And then we'll have validation. We can comment this out for now. So we need to send the data to the device. And logits, going to be our sorry, it's going to be our loss. Um, this is your basic training loop. So this, actually, that's more clear. So our logic will be batch channel, which is 3, which is our prediction for each channel, for each segmentation mask. Right, so then we take the max. So this will return, well, actually it should probably just, I think it just returns so where the predictions match the label, this is going to be total correct. Total pixels um, pixels oh, I need to compute the dice score too, so total loss, well, right, the loss is on a pixel basis, so we need to equal loss.item times yb, the number of pixels, where num_l is the number of elements in, it basically does height times width. So the loss for the epoch will be the total loss, which is the loss for that image times the number of pixels, right? Because loss is calculated. We're not doing image classification, we're doing pixel classification. So we need to multiply the loss times the total number of elements to get a sort of rough estimate for what the loss is on the pixel level. And then we divide that by the total number, by the total number of pixels. I guess, well, yeah, let's do it that way just in case. The size of the image shouldn't vary, so yeah, whatever. Um, um, let's just do this for now, and then we'll let's run this and see what we get. Something's oh, right. Train, correct. 0, train, total, 0, train, total, 0, 0. Loss, 0. Oh, train, total loss. Total, train total, train total loss. This organizes this a bit better. So train loss we use to calculate train epic loss. Train correct we use to calculate accuracy. Train total pixels we use to calculate epic loss and accuracy. And then yeah. Let's see. I can decrease the samples even more to make this run faster. Okay. Oh, I didn't print out anything, so first I'm going to update the progress bar with the loss. Then I'm going to write training loss, train epic loss. So let's see. What batch size am I using? Batch size, batch size. Why is it not? Oh, yeah. So update TQDM, the update. Hmm. Right. Set post fix. Why? Why is this going so slowly? These numbers look okay. It's hard to tell with such a small sample size, but nothing looks egregious, at least. This is running really slowly, really, really slowly. That looks okay. Train. Well, I'm just gonna copy. I'm gonna read. I'm basically redoing the copy, and I'm just redoing the replace because I can't remember if what I changed or what bugs were in the code that I actually fixed. So, um, okay, that should just work. This does not require graph. This, oh. Let's run this again. Okay, that looks like it works this time. Let's kill that training loop. Move on to the rest. One. We want to log it at the end of the epoch. So wandb. We want to log things to weights and biases, or log all the metrics to weights and biases. So let's just copy. So I just implemented that code. I'm not gonna type all that out. wandb finish. And this is our training loop. So I'm just going to pause here and then show you the fully implemented code next. But that's basically it. If you run that, I mean, maybe I'll read this over. I'll give this a once over on my own. I'll stop the recording and give it a once over. But I'm pretty sure if you run this, you know, just in terms of the training loop and the model that we have right now implemented, you can get, you know, a relatively decent dice score. It won't produce great segmentations yet, but it's heading in that direction. And now I'm gonna switch over to an implementation that has more of the server code implemented, so we can just start running it on the server, and logging things in weights and biases, and actually bringing up the dashboards to track the trading. And then we're gonna try to push this. We're gonna try to push the dice score as high as possible. Right now, currently, I'm at about close to 80, close to 0.80 dice, which it needs to. I need to get. I think to see the type of segmentations that I want to see, I need to get to like 85, I think, which we're gonna have to do some things. We're gonna have to do some things first, but yeah, that's the full implementation. Hope you enjoyed. So I'm gonna stop this video and then start recording another one. Oh, okay. So I created a pod. I set up the environment, and now I named the run UNet server video. And now I'm going to run with server configurations. And this will log, it'll create a run here in weights and biases for UNet server video. And I'll be able to differentiate between all of these different runs. It'll come up as a different color. So I'll start running this, and then, well, actually, let me make sure this works. Oh. Okay. Oh. Then install. Yeah. So okay, while that's installing, so these are the training metrics and these are the validation metrics. The one I care about the most right now is dice because I think it's a little bit more um, it's a little bit more optimal for assessing performance than accuracy. Like I said previously in the video, accuracy might be a bit biased because I think there are more, the number of background pixels are more dense than um, the actual thing to be classified, like the pets. So let's just talk about these runs briefly. The first run, the one in green, that I've done many more runs than this, but I deleted them all. The one in green is without any data augmentation. I don't remember what the ones in gray, and I'll probably just delete this, honestly. I think the one in red was with data augmentation, but without batch norm. And then the one in purple was with data augmentation and with batch normalization added. So you can see that without data augmentation, it converges to it converges the quickest to it converges more quickly to a higher dice score, and it seems like it seems like it's not quite overfitting yet. Actually it might be. It's a little unstable. Um but the reason why the dice score is so high is because there's no data augmentation. So it has it can learn the data more quickly, but it's not nearly as good as generalizing. Um, and then when we add data augmentation, so this red run, you can see that um, it doesn't it never quite gets as high. Well, sorry, the validation, the training diet, the so if we, okay, so let's look at the loss. So first we can see that it's overfitting, right? The training loss continues to go down, but I'd say right around here is where it starts to climb back up, and then we look at the dice and we can see that the optimal dice is right around this point. Right around this point. Right around epic 40, somewhere where this um um what would you call that? An inflection point. I forgot what you call that point, but and then if you look at the next run in purple, where we add batch normalization, it seems like it converges more quickly to it. It optimizes more quickly, and then it overfits, right? So it doesn't pass the dice ceiling of the red. They seem to be capped. It seems to be capped at a certain point around like 72, 73, 0.72, 0.73 in terms of the dice score, but it seems to reach that ceiling a bit more quickly, which I wonder why that is. Anyways, so let's see if this is done. It's not done installing. So just to sort of cut to the chase, I don't think that with this educational version of UNet on this data set, we're really going to get higher than the dice that we're seeing right now. I think in order to do that, we would need a much stronger encoder backbone. So I think some things I want to try. I don't know if I'm actually going to get to it for this educational implementation. So I think some things I want to try. Some things that I would try if I were to push this further. I wrote them down here. So more data augmentation. There's a library called augmentations. that will allow us to do more augmentations a little bit more easily. And then we can do weight decay, right? Learning rate scheduler, to hopefully, you know, we start with a higher learning rate, and then we decay the learning rate over time to hopefully smoothen out the training curve. We can do instance normalization and group normalization. I don't really know how much that would help. Dropout seems to help. You know, whenever you have overfitting, dropout is always a great go-to. And then I think the biggest thing on this list, which would give us the most gains, are swapping out the encoder for something like, let's say, like a pre-trained ResNet 34 on ImageNet. I think that would give us I think if we wanted to get mid to upper 80s, we would need to do step 5. I don't know if I want to do that for this educational version. Maybe let's just do a run so you can see it log in weights and biases. And then I want to run this load and test model. So as part of the code, right? So just to mention some of the additions that I didn't actually code in the previous in the video, I did add this load and test model. So if you go to this config and go to test model true, train model false, it'll instead of training the model, it'll load a saved model from weights and biases, right? And then it'll actually help you visualize how it's predicting the segmentation masks. So I added this bit of code here that will basically check to see if, you know, within a training iteration, if the dice score is better than the last dice score, then we write that model to weights and biases. And I'm actually thinking, because I'm running out of data, I should actually I should make an API call to delete the previous version, and write a new version and delete the previous version. And then when you run this when you change the configuration, set this test model to true, train model to false, it'll run load and test model, because you can see the main function here, right? It looks at the config variable, it'll run this, and it won't run the training. And then this just basically uses the API to grab the latest model, loads the weights into UNet, and then pulls visualized predictions, so that it'll use matplotlib to, you know, just create a plot of the ground truth image and then the predicted segmentation mask, and then it'll overlay it so you can see how well it's performing. Not to burst your bubble, but like I said, with this educational implementation, it's not doing too well, which maybe I'll pause the video, and then I'll do another run, save a model, and then load it in. I had to delete a bunch of models. I had to delete a bunch of models that I saved, and because I ran out of space. But then I tried to load one of the models and I was running into some error. I don't know. I'm just gonna do it. I'm just gonna do another run so you all can see it, and then load the model and test it out. So it looks like it's installed. So let's try to run this. How many virtual CPUs? Should be, 16? Interesting. So then I'm gonna need to virtual CPU, so number of workers. I need to do 7. I don't know why there are less CPUs. I don't remember configuring. Anyway. Artifacts. Wait, so this server. Unit server best model. Oh, all right, it has to download the data, of course. So this should be pulling this V107. I need to make sure that's a config variable. Artifact name. Oh, so this should work actually. Let's see where the server is. It's still downloading the data. Yeah, it looks like it's working. So let's see. Oh, so we can see it's, yeah, it's starting to make some contours and stuff. Let's see what, here we go. So we can definitely see it's starting to make some contours for sure, right? Even though it's not a full segmentation mask, it's still making contours. It's not, you know what I mean? It's, and we can see why the dice score is starting to get a bit high because there's still overlap. It's not, you know, at least the segmentation mask that's present isn't like outside of the boundaries of the ground truth segmentation mask. That's, well, why is it only showing 2 images? Okay, so let's look at what this run. So the run in oh yeah, I guess, yeah, okay, technically it did crash because I canceled the process. Oh. Runs. So UNet server batch norm. Let's take a look at what the predictions from the best model of this run looks like. None of these are great. Yeah, those are all pretty damn terrible. Definitely learning something. Some kind of contours. You can see it's learning some kind of contours. But yeah, this definitely isn't good. but there is some intelligence there. Yeah, you can see there's definitely intelligence there. It's just not great, which honestly is expected for this kind of educational implementation. But yeah, let's try to, I'm going to try to get the performance to be a little bit better, so we can have some more confidence in our model.